Hi there, I'm Dr. Ben Britton. This is my third lecture of an overview of focused ion beam microscopy. In this lecture we're going to explore focused ion beam milling and polishing of surfaces. Of course, I have to acknowledge significant input from a range of colleagues who have helped advise and share slides that have supported the generation of this slide deck. Hopefully you've had a chance to view lectures 1 and 2. If not, I'd strongly recommend that, although of course this does stand on its own to help you understand milling and polishing for focused ion beam methods. So, if we recall, we are going to use a fib to effectively have a focused probe of ions that enable us to effectively interact with the surface of a material, and that interaction can result in the formation of secondary electrons, somewhere over these secondary electrons, apologies. We can also produce ions, so positive and negative ions. We can also release neutral, and these could be single atoms, or they could be not single. We can also interact the gallium or the incident ion structure. We can interact that to neutralize the charge, and that can be useful to keep the ions hitting the same point so we don't get deflection or local lensing of the fib. We can also use the gas-assisted etching or deposition methods using the gas injection system to help modify the surface. That incident probe, not only will it eject some materials, so we'll get sputtering and secondary electron generation, but we'll also get interaction with the material. We can form defects in the material, we can get redeposition on the surface, and a few other bits and pieces. Now, we're going to use charged ions. We've seen in the previous lecture that these could be helium, gallium, should be gallium plus, apologies, or xenon in this case. The ion-matter interactions will create a few different parts in here. We can get imaging, channeling, sputtering, etc., and that enables us to do things like cut away the material in nanoscalpel or analytical approaches using secondary ion mass spectroscopy. So when we have that primary ion interacting with our material, we can have that primary ion being introduced in our vacuum chamber. It goes into our solids, and then we can effectively get that primary ion can move through the lattice. And so it's going to get knocked from site to site. At each individual knocking, it will reduce in energy. And one option is that primary ion will end up implanted in that material. What can also happen is that we can also, in that knocking, we can provide enough kinetic energy to displace atoms of the material. And so we can get those ions to displace, and those ions can be sputtered. And we can also sputter some of the implanted ions out again, and so we can reduce the total implantation. We also, as this process happens, will get the generation of so-called secondary electrons. Those secondary electrons can be very useful for, say, imaging or other electron-matter interactions. Now, the incident ion trajectories and interactions will depend on a range of factors. They'll depend, of course, on how fast or how much energy that primary ion has, what the species of that primary ion is. It will also matter how it hits the surface, so the surface angle with regards to the primary ion, and what this material is. So imagine this is a heavy material that's radiation hard. This primary ion will cause less damage in that case. So the interaction is going to be orientation and material dependent, and there are ways, if you so wish, that you can model these interactions. So we can use things like stopping range of ions in matter, SRIM codes, or molecular dynamics to really understand those processes as they progress. And this process will depend on the energy ion material and also the surface structure in these cases. So we see why this matters, because the incident ion can create a series of defects as it's going into our material. We can see that we can effectively get displacement of primary ions in the lattice, primary atoms or ions in the lattice. They can get knocked to secondary sites, and we can effectively form self-interstitials. We can also get those effectively sputtered and ejected out of our material. And we can also get the formation of implanted ions into that material. Now, this will happen at a relative temperature, and of course this lattice itself can repair itself. So there might be enough time, so although you get this collision cascade, actually the lattice can reconfigure, and effectively all of these atoms that were displaced can recombine and repair. Now, why is this important? Well, we're generating a series of point defects, say interstitials and other such, and vacancies. If we get a cluster of these, we can get radiation defects and we can get dislocations, so prismatic loops, both vacancy and interstitial loops. We can get implantation of the primary ions in this case. We can also get knocked in, so if we had a layered structure, we might actually have that layered structure could knock in. We can imagine that we could have a surface, say carbon layer, and this incident primary ion is knocking the carbon into that material. We can get amorphization, where this material, effectively the lattice gets gradually destroyed as we increase the dose to our sample. And we can get ion beam induced heating due to phonon interactions, where we get kinetic energy and heat. All these interactions are dependent on the temperature, the material is used, etc. But what we can get is, for instance, the creation in a TM lamellar, where we might have a surface layer that is amorphous. And that amorphous surface layer may not be interesting because it's not the structure we really want to look at. Now, of course, the size of this interaction volume is now dependent on the voltage. And so this is why we'll use a series of different voltages to enable us to polish this material, where we'll step down in voltages to reduce this surface amorphous and damaged layer. We can also get some cases where, for instance, if we have gallium, we might get alloying, and we can get aluminum gallium alloys, and that can, as indicated previously, give us grain boundary decoration and embrittlement in some systems. Now, ions and matter, there are a range of sort of ways that things interact. One of which to think about is how far does the ion stop? That's sort of one of the ways to control the interaction volume of the instant ion. And broadly speaking, we can see that the stopping power is tightly correlated with the, repeated 2 slides, apologies for this. In this case, stopping power is echoing the melting temperature of our system here. We can also look at the ion implantation depth for different ions going into our system and different substrates and different energies. So there's this nice modeling done by Cox, which is showing effectively in different systems that if we increase the implantation energy, we effectively get this sort of parabolic curve. But as we change the species of the instant ion and the substrate, we can also get a variation in the implantation depth. Please note that this is on a log y-axis, whereas this is a linear x-axis. This is in the calculations done here. This is effectively assuming sort of uniform across all different crystal orientations. You might get special cases, and we'll see this a bit later, related to, say, channeling in the crystal lattice. But the sort of rules of thumb is that higher energy, the ions will go deeper into the material. If the ions are smaller and lighter, they might go deeper into the system. If the substrate, apologies, is light, then the ions can go further because they lose less kinetic energy due to the momentum transfer of the interaction of the instant ion and the lattice. And also we might have effectively bigger instant ions will typically go less deep into our material for this. Now, in addition to what's happening for the primary beam going into the system, we can now have the instant beam going in, and we have a trough of material that's indicated in this beautiful cartoon. We have the instant ion, it hits the material, and it ejects. So we get sputtering from that system, we get an ejection plume. Now that sputtered material is pushed forwards, and therefore we get effectively the secondary ions that are then created and pushed forwards that then can go and deposit or interact with a secondary site. And we can get effectively a secondary redeposition. We get our first redeposition and our secondary redeposition. We can also get, effectively, we get another form of redeposition from the primary where it gets pushed forward, and we can get redeposition on the side of this. So So this is super important as we're trying to, for instance, cut to make this hole bigger. What we can see is that the path of this ion beam, if it started here, it's going to add and shallow and make this trench more shallow ahead of the beam. So we're going to worry about how we scan or raster the beam across the surface with regards to what the formation of redeposition is and where those ions are redistributed in that material. The sputtered yields in our system will depend effectively on the energy of this, but they'll also depend on the angle of the substrate. And so basically if we have a high angle, so the sample is an angle almost parallel, so in 0 the surface is perpendicular to the incident beam in 0. As we go up to 90, the beam is now almost glancing on that surface. And so we see a glancing surface gives us a significant enhancement of the sputter yield. This is going to be super important when we're polishing the surface of our materials. What we also have is that the implantation depth at higher angles is significantly lower. And again, that's very useful for polishing, especially of thin lamella or other such. Now, the sputtering yield is also dependent on the incident ion species. And so here, broadly, we can see xenon has a very high sputtering yield in silicon. As compared to, for instance, gallium, this is I think it's the light orange series in here. And then you have lower sputtering from argon, nitrogen, and oxygen in these systems. So this is kind of important with regards to the speed at which you can cut samples. So for instance, a plasma xenon fib can give you very high cutting rates. But other systems may be useful, as we'll see a bit later, for different applications depending on what you're doing. We see here, and I think I've sort of said this briefly, that broadly speaking, the sputtering yield is inversely proportional to the melting point of our system. And so we see here that effectively if it has a high melting point, then the sputter yield decreases. And that's why we would use, for instance, refractory metals like molybdenum as the apertures in our system. So we're going to have this incident probe, and one of the pieces we want to do is to make sure that our sort of knife is as sharp as possible. And we've seen that with a xenon fib, for instance, the probe current can vary from nanoamps up to, or picoamps in fact in some cases, up to microamps. And so here, if we just strike the probe for a very short period in a flat surface of silicon, we can see the probe shape by the kind of negative. And we see that increasing the probe current increases the probe shape. And hopefully it's reasonably well aligned, although it's harder to align very high currents in here. We have the shape of this probe. It forms some sort of Gaussian. In the xenon fibs, it has a relatively coarse beam tail. But why is this important for our machining process? Well, effectively, we're going to use this almost like a jackhammer at every single point. So we're going to take this, and we're going to then take this, and we're going to move the beam one site, and we're going to drill for a fixed period. We're going to dwell for that fixed period, and we hope that we effectively align our dwell points such that we get good overlap to create a line that builds up and cuts our material. So we can have some specific parameters. We can have the separation between the points. We can have the spot size, which is 2R in here, and we can have the overlap, which is in H. And we have the shape of the object, a length and width of what we're going to raster in this case. So we're going to spend a bit of time when we're operating the instrument to improve the focus of the beam, because that's going to be important as we overlap each individual dwell point to cut the sample well. And the focal quality will depend partially on the current and voltages, apertures and alignments of the system. We want to use a well-focused beam to build up our milling pattern by effectively move of the ion beam in this case. And then we want to move the ion beam through the system to have a nice path, and we're going to care about the path and overlap of sites and the dwell times, and these can be significant for the raster. Fortunately, this is a well-known problem, and so that well-known problem has been managed well by the manufacturers. And so, generally speaking, once you've got presets for the probe setup, most of these will be behaving themselves for most materials. It's only when things go wrong you might want to think about the raster geometry and probe settings that you're using for this. Now, one of the strategies that will be important is effectively how you're going to move the beam through the object. So we call this the scan or milling profile, and this effectively is the impact of the probe shape and scan strategy. Given that we know ahead of a hole, material will be ejected forwards and ejected around. So we want to think a little bit, imagine back to sitting on the beach as a child and digging a hole. You'll want to care about where you eject the sand to enable you to cut that hole. And so we can have effectively one method. The simplest and cheapest is just to scan in a line and then say go back to the left and scan in a line. It's kind of like an old-fashioned typewriter. Now at this you can see with the cursor that I have to fly back the beam. And so there can be, if you don't blank the beam quick enough, there can be incident ion damage as this beam is flying back. So we could change the system where we could have a zigzag where we scan and then we move up and we scan back and we move and we scan up. That's better, but effectively do bear in mind that the edges of this will have a different amount of dwell compared to the interior. So you might get some edge effects if you're not careful. Another one that could be useful effectively is you're going to dig and create your holes, but you're going to now scan in a spiral in morphology, or you can spiral out. And this will depend largely on where the material is being ejected and what surfaces you would like to have a very good quality. One critical aspect of all of these approaches will also be the shape of the probe, especially with regards to the so-called beam tails. And we just recognize that gallium beam tails are typically smaller than xenon tails, as we've described earlier. So we do spend a bit of time checking out that the beam is of a decent shape and size. And so there's often, prior to doing some significant work, we might align and check our presets for different settings in here. So we'll focus, stigmate, aperture, and improve and check the qualities of this. And in most modern instruments, there are automatic routines to enable this alignment to be done easily. You just effectively put a piece of silicon in and run the alignments. That's what I showed you. Actually, those holes were from an automated alignment set on our Amber X instrument. So once you've got that nice beam, effectively to get a good quality mill of your surface, you just want to have a careful understanding of the beam shape and scan strategy. Here you want to control the dose per point. That's important. Imagine that you're on the beach digging a hole and you want to dig a big trench. Do you dig for 10 minutes at each point, or do you dig for 1 minute, move to the next point and go through and then repeat your digging process? And you can imagine that could change how the material, the ejected material, is built up and scattered, and that can change how fast you cut through the object. This is really controlling that redeposition process in that system, and some of this is going to be the use of very, very fast beam blankers to help you to manage this as well as possible. So we can see this milling strategy. Effectively at every single point we create this sort of Gaussian profile. We're going to hopefully get that the material is going to cut this hole. Effectively we're going to get a negative of the total dose at each point for sputter. We're going to overlap our sight points quite nicely, so we can have that overlap of pitch to enable us to get a smooth surface, and we're going to control how we move the beam through our raster process. In addition, I should have mentioned that we can change how we cut. We can do something like a rectangle cut, and a rectangle cut can be nice, but you're going to get bits of effectively edges are going to look awkward. You might not want to or need to dig as deep the whole way through. For instance, if you want to look into a material, you might be able to use something like a stepped staircase. You could also use a gradient cut to cut out like a V shape. You could do a thin line, so the line enables you to have a little notch. That can be useful for a range of reasons, cutting and marking things, or cutting off objects, etc. Other areas you can do an annulus, so we can imagine that spiral in or spiral out, where we effectively are scanning in a circle. And we can also do this effectively not just with a circular annulus, but we could do it with a donut annulus. And we could leave material left in the center, such as in those CT or atom probe tomography specimens. So what we've got to just recognize is that as we do our milling process, we're going to have a series of different artifacts that can impact how good the surface looks, both in terms of the surface roughness, but also of the damage. So we're just going to go through all of these different examples: beam tails, curtaining, redeposition, shelf formation, channeling, implantation, amorphization, phase transformation and twinning, interface mixing, and heat damage. And we'll see examples of where this has happened in practice. So the beam tail effect is that we have effectively an angular spread of the beam, and that will create a slight rounding as we mill the surface. The rounding can be reduced if we put a deposited amorphous protection layer that can help us improve the quality of our cut as we remove one layer after another. So we might cap the material to improve the quality of the cross section. And we've actually seen this already in the lecture. If you saw that gallium arsenide thin layer structure, where the cap improved the quality of the cross section quite significantly. So the beam tails have a really high impact for high aspect ratio milling in this case. And to address this, we can use a protection layer. This protection layer could be introduced to something like the gas injection system, but we can actually use also more macroscopic protection layers. We, for instance, sputtered across the whole surface of our objects and materials, or we might deposit a layer of silicon, for instance, on top of the object to enable us to cap a large area quickly. What you can also do is you can actually back tilt or over tilt to reduce the final thinning steps. So if you know that you're going to get like a 1 degree curvature, you can tilt the sample backwards by -1 degree so that you can remove and flatten out to get parallel faces on your object. And that can be particularly useful, especially in TEM prep, TEM lamellar prep. For another artifact that it can exist is the so-called curtaining artifact. And this curtaining artifact occurs when you have a variation in radiation hardness across the surface of your material. So for instance, if you have a hard bit of material, you basically get a shadow that will start to create a sort of waterfall or curtain artifact ahead of it, where the material is not milled because this is radiation hard. We can see this example. So this is a cross section in some steel. We have a silicon wafer that's on the surface of this material. And we see here that the silicon wafer gives us a pretty nice protection on this top layer. But in the steel with a xenon fib, we now have significant curtains roughness due to the presence of grain boundaries and precipitates in this microstructure. There are ways, as we'll see a bit later, to improve and reduce the impact of curtains on the analysis that we look at. Do bear in mind this is a relatively large field of view that we're looking at. This is a 1.1 millimeter cross area. So depending on what you're looking at, these curtains may be or may not be important for your application. We've mentioned the impact of redeposition, and the redeposition is important with regards to how deep we want to cut the hole. So as we mill into the material gets ejected, some of this material will deposit nearby, but some of it will go back and start filling the trench. And this will be important with regards to the aspect ratio of the hole or trench that you're drilling. The deeper the aspect ratio, the more likely the redeposition is going to get in the way. So we can see that redeposition backfilling and effectively meaning that what you have cut is not the same shape as what you expect. Now, ways for us to improve this are that we can effectively scan the beam pushing forward to different depths so that effectively the redeposition is ejected forwards. When we mill at this point, then we're going to remove the redeposition, some's going to go backwards, but each time we're milling for an increased time, that enables us, by the time we're done, to have relatively little redeposition on the cross-sectional face of interest in the object. This redeposition can be seen in practice. This is a staircase-based mill, where we see effectively staircasing enables us to reduce the amount of redeposition, and this is then when we've got that redeposition that's backfilling, and we can see it's of a different composition because it's sort of got stuck inside the trench. This redeposition will depend on dose and current and a whole range of bits and pieces, but it's one of the most sort of artisanal and important aspects for you to control. Again, as mentioned, we can use sample tilt to control this a little bit, and we can also do low current and low kV cleanups to gently remove that redeposition layer as required. We also will have a strategy with regards to the milling direction and the aspect ratio of how we're going to manage, for instance, cutting a deep trench in our system. The redeposition artifacts can also give rise to what we colloquially in our group call a shelf. A shelf formation happens when you're doing typically a high aspect ratio cut, and this can be found, for instance, if we're doing a tomograph. So we have the cap that's present. We can effectively get that this surface is not quite removing, and we effectively, if we fib polish ahead, what can happen is if we cut this material, we leave behind a surface layer, a so-called shelf of material that will occlude and mess up and can fill in with redeposition. So here's the shelf. Typically, to address this, we make sure that we remove enough depth through our glancing incident cut every time we go through our material. We can also do a box polish to remove the redeposition and restart that polishing routine, but ultimately we have to make sure that we're not too impatient, that we remove enough per polishing step for our particular application to make sure we don't get this shelf forming ahead of where we're polishing. And this is worse for large depth or large aspect ratio cross sections, and especially is important in xenon fibs due to large beam tails that can exacerbate the formation of a shelf. We've seen that the ion beam itself can effectively create defects and ultimately create amorphous layers. Here we see that effectively the amount of amorphization is dependent on the total dose. We get some sort of initial linear region, and then it just becomes amorphous once you've just effectively moved all the atoms out of their lattice sites, their structural sites, and then moved them around and sort of messed up the soup of atoms in that material. So we get a saturation of the layer in here. Ultimately, if we have more dose, therefore we get more damage. But in addition, we can help reduce this by effectively reducing the kV of the final mill to start removing that amorphous layer. So we see as we go from 30 down to 5, the amorphous surface layer is starting to reduce incrementally in this case. One of the challenges is that fib performance is typically quite poor at low voltages, and so that creates some issues with regards to seeing what's going on for that polishing step. And so you might just have to sort of do it and trust it and try a few times until you sort of take the sample, say, to the TEM or STEM in SEM to see how well it looks at each time. We also saw that the ion beam damage is related to the angle of incidence of the sample, angle of incidence of the incident beam with regards to the sample, and so grazing angles can be very useful to reduce the ion beam damage because you're sort of tickling away that surface. One of the areas, and we'll see this example a bit later, is that you can also use a different beam to finish the sample. And so one example I'll show a bit later is that you can use, say, an argon ion beam to finish and tickle away the surface because that can create less damage, especially at low voltage, than our primary focused ion beam. The presence of this damaged layer can be quite important, especially for TEM lamellar, where you've prepared both surfaces. And here, effectively, it's going to be the fraction of the damaged layer to the undamaged surface, undamaged high-quality surface. And this will depend on where the information depth of our TEM foil comes from. We can see this as we move into material. So this is into a piece of silicon. Towards the surface, we get full amorphization. We can see that in the pseudo-diffraction, the diffraction pattern that's presented, we get a ring pattern. As we go from site B to site C, we see that we now still have rings, but we have now some spots, so we have some good lattice. As we go towards the interior of our object, we have beautiful crystalline, where we just see the diffraction spots appearing nicely here. So the ion beam damage can create an amorphous surface layer. We see a relatively amorphous transition layer, and then we have a crystalline subsurface. And the impact of this will depend on what you're doing with your experiments. This can be really important, for instance, if you're doing low kV transmission electron microscopy work, for instance with STEM in SEM work at 30 kV. This is super important as you're strategizing towards cutting and thinning cross sections. If you want your sample to be, say, 100 nanometers thick of good quality surface, you might want to have some sacrificial layer, say 40 nanometers on the top and the bottom, that you're going to thin using those low kV cuts to remove and reduce the thickness of the damage as you prepare the sample. We can see that this, all of these damage processes, this is going to be related to the voltage of the primary beam. And so here we see effectively the thickness of the amorphous layer can be reduced by reducing the primary fib beam. But in addition to amorphization, we can get ion implantation that can cause lattice swelling and also other doping effects, and also alloying that can be formed. But broadly speaking, we see that the amorphous layer thickness is proportional to the voltage quite nicely. Some sort of linear, maybe flattening off, depending on what we're doing here. We see this beautifully in this TM pictures where you have or STEM pictures where you have the high-REM images and then the amorphous surface layer. And this is looking at the impact on different substrates, which will have just slightly different thickness effects. This is a really nice paper to explore ion beam damage versus energy in these systems. What I would stress is that it is important to recognize that the amorphous is the first problem, but the second issue is effectively that you can get some impact, specifically lattice swelling, for instance, in the layer that is not amorphized, but can have incident ions being deposited in that region. We see this in particular if we are playing with different fib types, we'll get effectively different impact on our material, and we can see that associated with the damage below the cutting surfaces here. And we see this as we look from the amorphous to the transition region into the crystalline subsurface. And again, some beautiful work presented here. I mentioned one thing about gallium implantation. This is particularly important for anybody working on aluminum alloys because gallium is famous for forming an amalgam that attacks preferentially grain boundaries. And you see this with this cute little video that is showing that it embrittles grain boundaries in the top of a drinks can. So this is kind of important that you might want to care about the phase diagram of the instant ion and your target material just to check that nothing funky is happening. And so one area is that you want to be careful with the total dose and what you're looking at, but you might want to use perhaps a different ion to use on a different system or to tidy up with a different ion to reduce the gallium implantation issues and risk. The ion itself will also channel, and this is one example. It can be really useful to reveal grains of different orientations. This is an example where gallium has been used to image a polycrystal, and we can see beautiful grains as well as twin structure that's presented in here. And so like electrons, ions channel. This is very significant. This will impact not only the backscatter and secondary electron and secondary ion yields, but it will also impact how fast the material can be removed. And so this is both significant for imaging and milling, and it's going to be related to the crystal orientation and the sample tilt. This has particular issues. We can see that if we have a poor alignment of our silicon, we have a good alignment of our silicon. In the channeled case, we get beautiful edges. In the non-aligned case, we can get effectively that we get the squares aren't as square as they should be. And this can be very important if we want to look at the fidelity of how we cut objects on this system. The channeling will also impact the incident ion depth for where you get implantation in that system as well. The channeling can be useful, and I showed this a bit earlier. This is beautiful work from Cyril Langlois and colleagues, where effectively they've used ion blocking theory to create a pseudo-like EPSD technique, where they basically collect a series of raw images, rotating the sample with regards to the incident beam through a small circle, and you produce these blocking patterns. You can then match that up for the crystal orientations, and they worked out you could get something within like 5 degrees for the crystal orientation of your polycrystal object for this, so it's kind of fun. The ion beam can also cause phase transformations. This can be quite important in steel systems. And so here, effectively, if we're looking at and just using EBSD to identify the amount of phase that's been formed, we can see that as we increase the incident dose, so the coulombs of ions per unit area, we see that we get a more of the BCC phase that's presented. I think this is in steel in this case. And so for materials that can have an ion-induced phase transformation, we might have to care about this. And that can be important, as I say, in steels, but other systems as well. So it will be ion species, energy and dose, as well as material specific, but it's just to bear in mind that sample prep can always impact your material itself. In that vein, we've also seen in magnesium using too high a probe currents can result in the formation of nanoscale twins or microscale twins. So we see these like fat changing color in this image. We see them over here, where we see these twins that were not present prior. And those twins are basically because the material is heated up and been implanted, that we get stresses, and that you can get localized twinning around that. And this can cause both twinning and also detwinning, so you can remove structures in this, and that can be effectively due to a strain-enhanced deformation mode. We've seen this in magnesium, where we had to tune the fib conditions to avoid ion-induced defects associated with this tomography experiment. We were lifting out this cube to pull out and inspect. You can see the little nano indents, and we'll see this example a bit later in the lectures. The twinning can basically be reduced by careful fib control, and this was effectively, we did a series of prior tests to manage the probe current and scan strategies to optimize how we cut out and liberate this object. In some materials, we can also get localized heat damage associated with the primary ion causing phonon interactions, which cause you local heating, and that local heating can cause damaging of the surface. This is important, for instance, this is looking at a polymer electrolyte with a catalyst layer, and effectively there are very fine platinum particles in the catalyst, but if you don't do this properly, and there is heating damage, you can get effectively restructuring of the polymer, and you can see that the platinum can start redistributing and mess up what's going on. This is particularly important for soft matter and biosystems, and ways to address this are controlling how the scanning strategy is done, but also you can do localized sample cooling, so you can do things like cryo fib in those cases. This for polymers is very important. One of the things here is that kind of important in polymers, actually low kV ions can cause significant implantation in polymers. This can be seen where you can get a change in polymer properties. You can effectively see this in a phase shift from, I can't remember what it was doing, I think it was AFM or similar. You get a change in the properties depending on the low kV, gives you a significant change in both the roughness and properties of that system. So just to bear that in mind, that the ion beam damage in polymers can be quite significant if you're not careful. You can also get interfacial mixing, and so here we can effectively get platinum. For instance, if we do certain cases, we can do a deposition, and then the incident ion can effectively push the surface capped layer into the material. And so this can be like if we do a protective E-beam cap, we can push that in material and we get effectively a mixing of the interface. So the interface is blurred near surface due to effectively knock on when the primary ion has hit the material. If we have multi-phase materials, life becomes quite hard. And so here we can see that curtaining can be quite significant on multi-phase materials. It can matter quite significantly. It depends on what you're doing. But you can get effectively curtaining, you can get implantation, and you can get cracking. You can see cracking of interface grain boundaries here. You can also get significant drift issues. So this is showing the issues associated for a tomograph, where you have multiple phases and it's creating localized charging. It hasn't been compensated very well. And so here you have to use a software correction algorithm to get the reconstruction to behave itself. You can mitigate this with capping to try and protect the surface layer, but you can also reconsider how the surface and experiment is performed. There are a few ways to do this. But just to bear in mind that multi-phases get a bit harder. With this is why we tend to suggest that people practice on single-phase materials before moving into multi-phase systems. Other ways that we can reduce effectively damage is we can cool down the system, and we can use that using a so-called cryo stage. And so here effectively we can reduce the surface damage by effectively doing cryoplasma fib in this case. And this can be very important not only on damage in the surface, but it can also be important because actually the fib and other methods can push hydrogen into the system. Imagine that you've got a very thin layer of water on the surface. Most water gets everywhere. A very thin surface layer, effectively the incident ion and electron beam can push the hydrogen from that into your material, and if the hydrogen doesn't like playing nice, then the hydrogen can form a series of hydrides in some systems, like titanium and zirconium, and this can only be fixed if you have things like cryo to improve this. So just bear that in mind, that you might have surface-induced artifacts due to surface preparation with a fib, and hydrogen and hydrides are one particular challenge for certain material systems. So this was just a very sort of quick whistle-stop tour where we see a range of different defects. We have chemical modification, alloying and implantation. We can get point defects, Frenkel pair generation, and no recombination. We can get self-interstitials and vacancies. They can coalesce to form dislocations, etc. We can get damaged coalescence, and we can get amorphization, and this can give you also distortion of the lattice. We can get redeposition artifacts, so we can get sputtered material. We can then re-implant that sputtered material elsewhere, which can cause us some issues to alter the local structure and chemistry of our system. We can get ion beam induced transformations, so phase transformations, so austenite can decompose to a ferrite, for instance. We can also get twinning in some systems. We can get preferential sputtering, and that will change the local stoichiometry of our problem. And we can also get hydrogen ingress that can impact what's going on. So these are really important to bear in mind. There are a few other defects that exist, but this gives you some of those ideas and hopefully will help you address if you see them coming up, or if you see data later on. You're like, where did that come from? Was it induced from the fib itself? This is also a good point to just say with regards to, we've used the beam. We can use the beam and collect the ions, and so this is an example of a system based at I can't remember where it's based. I think probably Imperial College is where this photo is from. Maybe not in this. But here we effectively can put a SIMS instrument. This is a SIMS instrument, a secondary ion mass spectrometer, which can collect and work out what the ion species are in the sputtered cloud. The ions that are produced can be from the sputtering cloud can be positive and negative, and so it depends how you polarize the effectively the SIMS instrument to collect those two systems. There are some SIMS instruments with double heads that can collect the positive and negative cloud. The mass spectrometry can be used to characterize the ion yields. What's really cool about this method is it's a relatively good local probe, so you can basically get quite high spatial resolution because the primary ion beam is a tightly focused area. It's also super good. It's one of the few methods that can relatively easily detect lithium. Most of the other methods require you to have lithium metal. If you have lithium 1+, then you don't actually have enough electrons to produce interesting signals for EDS or similar. So you can get light element resolution of lithium ion, so good for battery systems, and it's very surface sensitive. One of the big challenges though is that the primary ion beam can cause effectively variations in the location of where that material sputtered. So you have to actually do quite a lot of calibration work. Some people have AFMs coupled into their fib SIMS instruments to enable you to characterize where the material was sputtered from. It can be relatively slow to access large volumes, and there is a limited number of ions in the ion cloud that can affect detector efficiencies. And this will give you a variation in the ion yield and detection of different species, and that can be important in terms of trying to quant this. So you spend a lot of time calibrating your system. And that's why I say calibration is really important for you to really have confidence if you're going to use fib SIMS systems. But this can be kind of nice, is that effectively you can set up to have your floating SIMS optics, where you basically have the primary beam comes in, creates this ions that then go through a series of accelerating plates and transfer optics, and then they can move into a magnetic sensor to measure on a focal plane detector. There are other ways that you can collect ions. You can use ion channel plates and mass spectrometry. There are a few others as well if people want to start playing with ion beam instruments. But often, actually in practice, a huge amount of our ion beam interactions are actually characterized through the secondary electron detection, where the ET detector can be used to see how the primary beam has interacted with the surface of our material. And so actually we can image in real time as the fib is moving, how many secondary electrons are being collected, and that's very powerful for methods. But the SIMS-based approach does enable us to have effectively, we can scan across our material, collect the TOF SIMS data, get the mass spectra, arrange it, and characterize the ions for that nicely. You can do depth profile by being very careful of how you do this. And once you do this, you can then build up a total sort of volume to image and understand material systems. And again, I stress this can be very nice for things like battery materials in particular, if done carefully. So hopefully at the end of lecture 3, I provided you with some overviews of milling and polishing approaches, where we see that milling And polishing can give you significant ion matter interactions, and that will vary depending on the ion that's present, the material and the surface. The artifacts themselves can be minimized depending on the end goal of the experiment, and so you might structure to do a series of different stages to mill or prepare surfaces. These artifacts will also vary due to the operating conditions, the ion type and the sample type. Generally speaking, you can probably borrow a lot of conditions from a sibling experiment prior to applying it to your material system. And most people who have got a fib have a reasonable amount of experience of these things, or you can ask the manufacturer and their applications team for some advice when required. So that brings us to the conclusion of Lecture 3. In Lecture 4, I'm going to look at more detail of the gas injection system that's going to be used for deposition and etching of our materials.